Let's take a look at the process of multiplying polynomials when both of the polynomials have more than one term. So in the first example here, we have a pair of binomials. Both of these have more than one term. Both of them have two terms. And I'd like to multiply them together in an appropriate way. We saw in part 1 that distributing a factor across terms is something that we can do, and I can think of either of these as a factor multiplied with the other. So I can distribute, for example, I can distribute 2 times a plus 8. I can distribute that to each of the terms in the other polynomial. So I get 2a plus 8, I want to keep it in parentheses for a moment, multiplied by 5a, and then minus 2a plus 8 times 3. But now we can distribute again. This time the 5a can distribute to each of the terms inside the polynomial 2a plus 8, and also the 3a can distribute to each of the terms here. So 5a times 2a, let me write that down bit by bit, 5a times 2a plus 5a times 8, and then I get a minus 2a times 3, and 8 times 3, I'm going to be a little bit careful here because of the negative sign. The negative sign, because of the way the parentheses are set up, the negative sign actually it applies to both of these terms as well. Another way to kind of think about this, we multiplied 2a plus 8 times minus 3, is that minus 3, that negative 3, needs to multiply with both of those terms. So this is actually going to be a minus 8 times 3. Right? Essentially we have a negative 3 times a positive 8, so it should be a negative result. So multiplying together now, these monomials, I get 10a squared plus 40a minus 6a minus 24. And the two middle terms here are like terms. They have the same variable raised to the same power. So we can finish our problem and simplify by gathering them together. So I have 10a squared plus 34a, 40 minus 6, minus 24. And that would be the final answer, the polynomial that's the product of these two. I do want to mention something about the process here. So distributing the first polynomial to the terms of the second, across the terms of the second, and then distributing those terms, the 5a and the 3, across the terms of the first, essentially what we want to do is we want to make sure that every term from the first polynomial gets multiplied with the terms of the second polynomial. So I want to make sure that 2a is multiplied with 5a, and also that 2a is multiplied with negative 3. And I want to make sure that 8 is multiplied with 5a, and that 8 is multiplied with negative 3. So, distributing one polynomial across the other, we just want to make sure, at the heart of it, we want to make sure that every term from the first polynomial is multiplied with every term from the second polynomial. A second example brings up a notational issue that's important to see. M plus 3 squared, squaring exponents, in general they represent repeated multiplication. So in order to find the polynomial represented by that expression, let me write out m plus 3 times m plus 3. The square tells me that I'm taking that exact same expression, m plus 3, and multiplying it with itself. So thinking about what I just said, essentially what I want to make sure happens, I want to make sure that the m from the first polynomial is multiplied with the m and also with the 3 from the second polynomial. So two terms that are going to be part of my final answer are m times m, so that'll become m squared, and m times 3. But I also want to make sure that the 3 from the first polynomial is multiplied with the m and also with the 3 of the second polynomial. So I get a plus 3 times m and plus 9, plus 3 squared. So the m times m is going to be m squared, And now the middle terms, usually we write the numbers in front. So m times 3, that's the same as 3 times m. But then we also have another 3 times m, and the 3 squared, the 9. So the 3m's, we can gather those together, and we get m squared plus 6m plus 9. One of the important things to realize, something that is definitely an indicator of your algebraic sophistication, it's important to realize that exponents, they don't distribute across to different terms. They don't distribute across addition or subtraction. Exponents, they do distribute across multiplication, but that's because exponents describe repeated multiplication. They don't distribute across addition or subtraction. So let me end. We'll look at one more example, but I'll let you kind of think about it for a moment first. So let me give you this question. Take a moment, pause the video, and try to multiply together 2x plus y and y squared plus 3xy plus x squared. So in a moment or two, I'll walk through the answer here. I'll talk about the answer. But I encourage you to pause the video for a moment and try to come up with the solution on your own first. Alright, I hope you took some time to pause the video and find an answer. Let's talk about the process of multiplying this out. So we could walk through the process, as we did in this first example, and write 2x plus y next to each of those terms. I'm going to do what we did in the second example and think of it kind of in the more general way, where what I'd like, what this means, I'd like each of the terms of the first polynomial to multiply with each of the terms of the second polynomial. So the 2x, I want that to multiply with y squared, and also with 3x times y, and also with x squared. And then I want the y to multiply with y squared, and also with 3x times y, and also with x squared. So let's write that out, and maybe I'll use the colors here to do that. So 2x times y squared, that'll be 2xy squared. 2x times 3x times y, that'll be 6x squared times y. And 2x times x squared will be 2x cubed. Working with y, if I take y times y squared, I get y cubed. Y times 3 times x times y, I get 3x times y squared. And finally, y times x squared is just going to be y x squared. Now, to come up with our final answer, we want to look at these terms and see if there are any like terms. Any terms that have the same variables raised to the same powers. And it turns out that there are. I have an x times y squared term and another x times y squared term. And it's a little sneaky here, but I also have an x squared y term, and yx squared is really that same thing. The order is different, but we have the same variables. Y is raised to the first power, and x is raised to the second power. So we have the same variables raised to the same exponents. So to simplify our answer, 2 and 3, I can put those together. I get 5xy squared. And then 6 and 1 more gives me 7x squared y. And then finally we have 2x cubed and y cubed. And so it's perfectly okay to kind of write those terms in a different order. They would represent the same amount. They're all degree 3 terms, so we can't really write them in like a descending order but by degree. They all have the same degree. So any order is really okay. And there's our final answer. I hope you enjoyed the video. Thanks for watching.